Welcome to Hidden Layers, where we explore the people and the tech behind artificial intelligence. I'm your host, Ron Green, and I'm very happy to be joined today by Dr. Sanjeev Namjoshi. Together, we're going to talk about topics at the intersection of neuroscience and artificial intelligence and get a sneak peek into his upcoming books on active inference and the free energy principle. Sanjeev is a machine learning engineer at Versus AI. He holds a PhD in neuroscience from the University of Texas at Austin. His theoretical research interests lie at the intersection of neuroscience and machine learning and their application to the computational modeling and simulation of living systems. Sanjeev has extensive research experience in machine learning, computer vision, computational neuroscience, bioinformatics, and molecular biology. He's currently writing 2 books to be published by MIT Press on interrelated approaches to modeling self-organized and adaptive systems based on active inference. Welcome, Sanjeev.
Great. Thank you so much, Ron, for inviting me.
Let's kick off by talking a little bit about how you got interested in pursuing a career at the intersection of neuroscience and artificial intelligence.
Yeah, so that's a great question. So I've had a very meandering path. I actually didn't discover active inference until I was in my first postdoc, and even though I was already in the neuroscience field. And I think if we go back to, really go back to undergrad when I was starting to get into science and thinking about what I wanted to do, I originally started in molecular biology, but I already knew that I really wanted to study something where I could look at and understand some of the deeper philosophical questions around human nature and the human lived experience. And I didn't know what that was yet, but as I ended up in molecular biology, I was actually studying yeast genetics for 3 years in graduate school before I switched into neuroscience. And it was at that point that I started figuring out what I really wanted to do. But I also had a deep interest in mathematics. And all of these things didn't really come together until I was actually ready to leave academia, and I was writing a grant, and it was something I didn't want to do. I didn't know exactly where I was going to go, but I thought it was machine learning. And then I found this paper by Carl Friston, who we'll talk about soon, called Life as We Know It, which at this point, the field has taken that paper and moved further along in the evolution of these ideas. But it's a beautiful and wonderfully written paper, and it essentially, that moment, I saw all of my interests coming together. And then going into machine learning, I've kind of moved through all of that until I'm now at Versus, where those interests have now collided.
I'm lucky enough to have had a early peek at your book, at the first volume of your book, which is coming out later this year, on active inference and the free energy principle. Let's start there. What is active inference? What is the free energy principle, and how do they apply to neuroscience and artificial intelligence?
Right. Yeah. So starting with active inference was created. It's a field of computational neuroscience that was created by Dr. Carl Friston, neuroscientist working at University College London in UK, and he basically took some of the ideas that already existed in computational neuroscience, going back. Really, it goes back to around 1880s with Helmholtz, which is this idea. It's called perception as inference. And later, as it kind of evolved, Richard Gregory was most famous in the 1980s for this idea of a hypothesis testing brain.
Right.
Yeah. And active inference kind of takes a lot of that lineage, plus a lot of other fields that came together around this Bayesian brain hypothesis, which I'll describe in a moment. And active inference kind of comes out of this framework. So it's a way of describing human and animal behavior from the perspective of Bayesian inference, but it's not purely just computational. It also includes a lot of the neurobiology and scientific research that has gone into all these fields.
Meaning it's not just a potential theory, it's actually grounded in some of our understanding of the biology of the brain.
Absolutely. And that means there's a couple ways to look at it. You can look at it from the biological plausibility angle, but also from the ML angle. It doesn't really matter if it's plausible. Does it do things we want it to do, right?
Right. Is it useful?
So there's different camps. Depending on where you're looking at, you can kind of interpret it in a bit of a different way.
Okay. I'm really fascinated that it goes all the way back to the 1880s. I had not heard that before. I thought it was a much, much more, I realize it's not the current conception, but that the grains of it would go back that far. That's really fascinating.
Yeah.
So I wanted to ask you, so the idea in active inference is it suggests that the brain is, constantly making predictions and updating its internal model based on how sensory inputs differ from predictions and sensory input. I'm kind of curious, how is that related to the idea that mammals, humans, and other type of mammals really enjoy being surprised? The idea that subverted expectations are maybe at the heart of humor.
Yeah, so that's a really, really important and interesting question. And I think when I think about human behavior, I think that aspect of it is, to me, the most fascinating and interesting. We haven't really gone into all the details of the kind of mechanism behind active inference, but just to as a prelude to that, when you talk about surprise minimization, surprise actually has a technical meaning in information theory, but you can think of it generally in the psychological sense. Minimizing surprise is kind of the name of the game in active inference. You want to be predicting really well, which means you're not surprised by the sensory information you're receiving.
Right.
So then you think about exactly what you asked, like, what about humor? There's so many other examples like magic tricks and, things we engage in where our expectations are subverted.
Right.
I'm going to speculate here. This is, piecing together some things that I think are really interesting to give a response to this. And I think the first thing that comes to mind is curiosity is a natural part of human behavior, and it's built into the core of active inference. This intrinsic motivation,
right,
where you go after things just for the motivation of just exploring the unknown and unobserved things in the environment.
Right.
And that also applies to emotion. So, dopamines will spike in response to unexpected emotional events. And not all emotions have this utilitarian survival value. We have things like fascination, insight, and curiosity, where we want to learn more, and that's an exciting feeling.
Right.
So we have that on one side. And then when you look at the other end of it, you start thinking about the ability to experience surprise in a comforting setting, because not all surprise is good. I mean, there's
absolutely
pranks can go wrong. There's fraud and people conning you. That's never a good surprise, right? But when we simulate in our brain, we simulate these extra possibilities that we've never seen before. So what would happen if I explored this unknown thing? And I think that the idea of subverting expectations is a way of exploring those unknown possibilities that are out there in a way that is safe and simulated. In the same way we have art and storytelling, these sorts of are other ways of experiencing others' emotions and other things that we can't do. And some people are risk takers. They'll go and they want to do the crazy things. Others will read about it in a book and they get the thrill out of that.
Right. I remember the first time I stumbled upon active inference, and it felt so right to me because it explained to me in a real unifying way a bunch of disparate things about human beings that felt very odd. Like you named some of them. The idea that we enjoy being surprised and we might find it humorous. Even sometimes when you get surprised, you think about like a jump cut in a scary movie. It's surprising in a different way, but it still kind of can be thrilling, right? In a controlled environment. And the idea that through active inference, the classic example that I always think about is like maybe a snake flicking its tongue, sensing the air around it to provide sensory input. To me, that is a really compelling argument that why we love to learn, why we enjoy surprises, why exploration is sort of baked into human nature is because it's a very positive, evolutionarily selected behavior, and our brains as prediction engines are at the heart of that.
Absolutely. I think that's you can motivate, we haven't actually gotten into the free energy principle yet, but you can motivate these ideas from the perspective of evolution as well.
Okay, let's do it. Let's do that now. Let's jump into the free energy principle. I'd love that. And then then tie that back into the evolutionary you thought you were going with.
Okay, yeah. And I'll also tie it back to active inference too,
okay,
so we can have all this together here. So the free energy principle, I like to think of it as more of it's based in statistical physics. Okay. So it's kind of the overarching background assumptions out of which active inference ideas come from. So, active inference is really focused mainly on animal and human behavior, particularly things that have brains. when you talk about the free energy principle, you're talking more broadly about the survivability of living systems. So that will key into evolution in a moment. So before I can really talk about that, though, I have to go into a little bit about mechanisms involved in active inference. I mentioned it was Bayesian inference, and Bayesian inference in this context means that we have some prior information about what the world is like. And that prior information, it makes sense. Reconstructing the world from scratch every time would be inefficient. If you want to, right? If you want to make quick decisions, right? The world has so much structure to it, and the laws of physics don't change. You can leverage that. The interesting part of it is that everything becomes an expectation. So it's all about a prediction that you think the world is going to be like, and you have sensory data that you combine with that, and you are able to use that to then infer or guess what's the most likely state of something unknown out there that I don't yet know. And that's the process of Bayesian inference. But in the exact case, computationally, it's usually intractable, especially if you want to make quick decisions. There's no way to do it in a world that changes like the one we live in. So that means you need to propose some approximate way to make that inference work. And variational free energy is an objective function that's introduced as a way to make that approximation happen. So when it's minimized, you are able, the minima tells you what's your best guess about what's going on out there. So when we talk about the free energy principle, we're taking that idea of variational free energy minimization, which tells us what's going on outside there. And we're saying that if we minimize variational free energy, we get everything else out of it. We can get perception, learning, attention, planning, and decision-making. All these things come back together under this one umbrella. So that's one aspect of the free energy principle, meaning active inference encompasses all those things, and the mechanism is minimize free energy to do that. So it's a form of approximate Bayesian inference. So going back to what you were asking earlier, that's the way that what the value of the free energy principle is to talk about now, what do we know about living systems that are minimizing variational free energy? So under the free energy principle, we would say it's kind of a reductio ad absurdum argument, which is, well, things that exist and are alive, they must be minimizing variational free energy, because if they weren't, they would be dead. That's the heuristic argument, just kind of giving the general one. Now the field has evolved into a whole new field, which is the subject of the second book, called Bayesian mechanics, which tries to formalize that concept in statistical physics to say, we are constituted particles that are organized in this way, and we want to avoid thermal equilibrium. So what are we doing as these living systems to avoid that? Well, the argument is we're minimizing variational free energy, we're predicting what's going to come next, and that helps us survive. But on the population level, the population has its own free energy minima as well. So different groups in their eco-niches, their different ecologically adapted environments they're in, they all have separate free energy minima that's local to those areas. And so you can create kind of a evolutionary variational free energy principle as well.
Okay. So I'm not sure if you can explain this without using a whiteboard, but maybe take a stab at explaining when you say minimizing free energy, what is the physical process behind that, or to the extent that we understand the physical process so far?
So the formal name in the field is called recognition dynamics. So it's a way of specifying how is neural activity in the brain changing in response to information. So the change in neural activity which can be encoded in various ways with different types of signals we can measure. That change in activity is a minimization of a calculated quantity that we call variational free energy. So it's literally saying that the brain is calculating that quantity, and it's trying to minimize its actual value. And the states encoded or represented in the different neurons in the brain are changing in a particular way such that variational free energy, which can be computed by populations of neurons, is actually minimized.
Okay. And just to dig into that just a little bit more to make sure I understand, you are measuring the signal on individual neurons or collections of neurons, and is the idea that there is a delta between that signal and some sensory input or something like that and that difference is trying to be minimized? That's
correct. So I think the one important thing to take a step back and talk about is the fact that your brain, the way we think of it in this field, is a generative model, and
Right.
that means something very specific here. We mean a joint distribution of observed and unobserved variables, but it's a probability distribution about your beliefs about states of the world and sensory data. So that means you can generate predictions about what you expect the world is like, and that's what you actually experience. You don't experience the world itself and the sensory signal, which is crazy because it means that, what you think, what you expect the world to be like, you make your own reality. And we all have different generative models in our minds that create different realities of what we think the world is like.
On that, really quickly, just make sure I understand that as well. Are you familiar with the video where people are passing a ball around and the gorilla walks through the group and you don't see it the first time you see the video? Is that an example of what you're talking about, where you don't really perceive the world raw? You're generating a construction of the world.
Yeah, so I think that's a good example of something like that. I think that would also fall into like attention mechanisms, which are also, it's kind of gaining synaptic gain. So like how much gaining you put about looking at noise, you're focusing your attention on certain areas of a visual stream, and you may forget other information because you're so highly focused on it.
Gotcha.
You can still motivate that in this kind of a language too, with free energy minimization as well, if you wanted to.
Okay.
So getting back to your question, the field of predictive coding predates active inference, and it has its origins in signal processing and information theory and other things like that, video compression. And the name of the game here is the different layers of your cortex are constantly trying to predict the layer below. So they're saying, I expect as a top-down prior, what do I think is going to come in next as input? And the layer below does that. When you get to the bottom, well, the very bottom is the actual sensory stream from your senses themselves. And so you have a top-down guess about what you're expecting, and you meet the actual sensory information. So this is encoded in populations of neurons in the cortex. So it's not just like one neuron. It's a whole system of neurons that would be doing this. And then the mismatch that you get is a prediction error. And in this case, it's a sensory prediction error. So you thought this was a sensation you were going to receive because of your prediction. Now you're seeing what it is. So that difference is encoded in other neurons, error neurons. And this speaks to the really extreme importance of information theory when we talk about compression. We talk about what information is in the formal sense.
Right.
It's what's unexplained, right? You don't care about what you already know because it's already there in your model, right? What haven't you explained yet? And you try to reduce that uncertainty. So all that's passed up is an error signal, and it then updates all the layers going up, and your model now conforms closer to the actual world. So the world is your training set, is one way to think of it. You're constantly updating your predictions based on what sensory experiences you're getting. There's more complication in that because we often know that we don't always believe what we see. Data can be noisy. There are reasons to ignore it. People don't change their mind. That's all these other layers that are on top there. But the fundamental mechanism, that's essentially what the differences that are being compared are.
I can't help but kind of think about the idea that we think of young children as just being amazed by the world, and then you lose that wonder as you become an adult. Maybe that's partly just because your internal model is getting pretty good, right? And so it's sort of a natural progression. I wanted to ask you about the free energy principle. So in traditional cognitive science, it sort of emphasizes the brain's role as processing information. In contrast, the free energy principle positions the brain more as a prediction generator. So how does that shift our understanding of the brain function? Because those are pretty radically different perspectives.
Yes, absolutely. And to be clear, like this isn't a completely accepted view in neuroscience yet. So there are a lot of people studying this particular view, but it's one among many, and it's becoming more and more popular now as more data is coming out and people are testing it in specific situations. But the potential that's really, really interesting here is, as we were talking about earlier, your expectation is what drives your experience of the world. And so the one thing about this that's really, really subtle is we are beings that go out in search of sensory evidence that confirms our own models of the world.
Right.
So we're not like scientists. We're not going out there. It is a hypothesis testing brain, but we're not doing it in this like blind way. we're looking for things that tell us we're right, essentially. So there's all kinds of psychological implications here, but there's two ways to look at it. One we already talked about, which is you use a sensory data to make your brain conform to the world, make it closer and closer approximation to the real world.
Your internal model.
Internal model matches the real world, your representation of the world.
Right.
Meaning the brain, we talk about the brain as being a model, or at least it behaves as if it is, well, depending on where your stance is philosophically. So when you take actions, because we haven't really talked about the action part of this yet, which is really important here, that's active inference, is you make the world conform to your brain. You expect the world to be a certain way, so then you go out and change the world in a particular way so that it conforms to your expectations. So a really simple example is when you eat food, right? From your brain's perspective, your body is part of the world. It's separate from your brain. And your brain has these certain set points or bounds. Blood glucose needs to be in this certain range. And it suddenly starts getting these sensory inputs from the body, which says, hey, blood glucose has fallen. So now you have a prediction error. Your blood glucose is much lower than your brain expects it to be because your brain has a prediction. I predict it to be in this range. And you know from prior experience that if you went out now into the world and you ate food, you took those actions, you would get rid of that error. So you make your prediction a reality by going out and doing that. And you eat the food, your blood glucose goes back up, and your brain says, great, now we've eliminated that prediction error.
Right. You've closed the loop.
Close that loop. And you can just imagine, for things like trauma, for example, you start people who are traumatized or have experienced PTSD, they will repeatedly experience these things that because they're reliving the expectation, the world is now a scary place. The sound of that car horn is not, you're not in a war zone anymore. You're just on the street, but you're primed to now expect to see the world in this really dangerous way. So all the signals you receive may still trigger and elicit certain responses in you. So there's a very wide literature in active inference on how different aspects of mental health and other types of aspects of brain function fit into this paradigm.
Okay. It's fascinating. On that topic, so the idea that, active inference is, this model where decision-making is trying to select actions that minimize expected free energy. Mm-hmm. How does that play against traditional models of the brain as sort of like this deliberation, this deliberative process, where you are thinking rationally and making, free will comes into it. I don't know if you want to touch on that as well, but, all of these kind of intersections are at play here.
Yeah, so traditionally we talk about rationality. It's comes from either like the literature in economics, in decision making under uncertainty, right. Von Neumann and Morgenstein's classic work, and so we talk about it in the sense of expected utility theory, which it turns out that active inference under certain specific assumptions is compatible with expected utility theory. One major difference is that a lot of work in behavioral economics has shown that at least if we describe rational behavior as in monetary sense or maximizing reward, that is still compatible with active inference. But now all the other behavioral effects, like when we think about the types of rewards that we maximize, they're not always monetary. Sometimes there's social cohesion. There's other types of things that we might want to maximize that active inference allows us to incorporate. And the problem, and actually deliberation too, expected free energy calculations, which is what is free energy like in the future? You're predicting because you don't know yet. These are unobserved states. You are actually in the actual computations, you're creating little what if counterfactual paths. You're saying, if I did this is what sensory input I would get. If I did this after that, and then you can compare all those branches by averaging the expected free energy for each one. And that's essentially what the theory is of what planning in the brain is to a really large temporal horizon. So we are doing this sort of deliberative planning. The real key comes in when you consider that the brain is technically Bayes optimal, but the problem is that we cannot be rational agents because we don't have enough time. We are bounded rational agents.
Right, meaning we can't think through the perfect next action constantly.
Not unless, we are creating a society for ourselves where that's possible because all of our basic needs are taken care of, right? But our brains have not changed in any evolutionary sense for 40,000 years.
Right.
And you imagine you're out in a forest and you look in a field and you see 25 rabbits. The next day you see 5. Well, you could make some theory about, random sampling and probability and whatever, but it's much safer just to say, well, there's a predator out there. I'm going to escape and just go. And so a lot of our heuristics and the biases that we have come from a survival instinct. And that underscores the fact that the rational part of our brain, really what it is we're not trying to model the world perfectly. We're modeling it in a way insofar as that it helps us survive.
Right.
And that's the practical nature of it.
Absolutely. If you think you might have seen a tiger, it's better to have been wrong about that, right? And have an overly heightened sense of fear than to guess wrong once.
Right. Because then you're dead. And then,
dead.
Then if you want to be, more reductive here, then you're not minimizing variational free energy, right? So you would not be alive to say that you did that. So it's kind of, that's how it all sort of ties in back to that.
Okay, great. All right. Well, as a machine learning practitioner working, in the AI field, principally with deep learning techniques, the idea that you are trying to make a prediction, that you are going to measure the difference between that prediction and the correct outcome, the actual reality of that, and then minimize that difference. Well, you're speaking my language. That makes perfect sense. Mm-hmm. Do we understand, within the deep learning world, within artificial intelligence, we're using backpropagation to minimize that error. Do we understand how the brain is minimizing that prediction reality difference?
Yeah. So, there's no evidence so far the brain uses backpropagation, right? So this is usually, it's called predictive coding, is the actual term of what's going on, the recognition dynamics that I referred to earlier, this change of gradient that's happening on all the different layers of the brain. That essentially is a predictive coding type of architecture. Active inference adds action to that story, and also a couple other bells and whistles that makes it a more complicated, more universal kind of model beyond what predictive coding is saying. But the core actual learning, or I should say not learning is not the right word, but the updating rule is that error minimization, where you pass the errors up the chain of the hierarchy to try to minimize prediction error. And the thing that's confusing about it is you have two-way messages. You have downward-facing messages that are coming, or up, top-down messages, and you have bottom-up signals. Right. So you actually have things moving in two directions, gradients being updated simultaneously. So it isn't exactly, you can't use, for example, just classic backpropagation to do that. You end up having these sort of state dependencies and things like that come into play.
Really quickly, I understand how the top-down signal might be corrected, because that's where the sort of the prediction is meeting the incoming sensor input. How are the signals going up being changed? That's interesting.
Yeah. So the way it works is they're usually called autonomous states in active inference, is what the name of the actual types of states that you're talking about here. So essentially, when you go up one layer, information about from the sensory information is sent up to the layer above and becomes like a sensory input to the next layer. So it's treated like it's a sensory input when really it's actually it's a signal the brain is actually generating itself.
Okay.
So it's like saying, on this layer of the hierarchy, using my model, I'm going to simulate what the sensory signal would be.
Okay.
And then you get that same error. And then you go up the next level, because you kind of have these layers of abstraction as you go up. So the brain doesn't have the sensory data anymore. It only has a representation of the next layer of what that data would look like in this hierarchical chain.
Okay. Does that help? To stay on that point for just a second more, does that help? Is it part of that trying to fine tune the sensory inputs in any way, or is it just about interpreting the sensory inputs?
So the process of fine tuning, you mean actually changing what sensory data you get?
Yes, on the signal coming up.
That's more when we talk more about action, which is kind of action happens. That's all kind of built into this. So it's hard to really talk about without really going into action. And the active inference part, you take when you compute expected free energy, there are different ways to formulate it, but some ways you can look at it is you're specifying a preferred state, a preferred set of states and observations that your target distribution you want to get to. So there's no actual cost functions per se. It's more of a distribution that you want to end up in. Okay. And there's trajectories you need to take of sequences of actions to get there.
Okay.
So there is a sense in which like you optimize the actual sensory data itself, but that's more on the action side.
Okay, that makes perfect sense. Okay, great.
And so just to kind of close that up, then, predictive coding, you can see that backpropagation is a special case of predictive coding. Okay. So it's a more general theory in terms of gradient-based learning methods.
Okay. Deep learning is by far the dominant technique within artificial intelligence right now. And I'm kind of curious, is it possible that the brain uses active inference in, the minimization of free energy, but that deep learning might be a better approach for developing AI or AGI in the same way that, jets don't flap their wings to fly because, we were able to develop flying vehicles without being constrained by certain evolutionary processes the way, obviously birds and other flying animals were. So is it possible that it's different, but maybe a more streamlined way to achieve intelligence? Or are there aspects to active inference and the way the brain works that are more powerful, more generalizable?
Yeah, that's a really great question, because I think it's always good to think about why are we using the methods we're using instead of just blindly applying the most exciting thing you can see.
Right.
And I think one of there are many different, I think, interpretations of this question. And the way that I like to look at it is that what is the right tool for the job? What are you trying to do? If you're trying to achieve human-like intelligence, usually we call that like natural intelligence. It's kind of a contrast to artificial, meaning like natural, inspired by human and animal behavior. You would want to look at the brain because it has already done that. It has already solved it. It's the most complicated system that we know of, and it has successfully solved that problem. And we don't have to take every single thing that it does when we make our models. We can look at it, what is it doing well, and we can take those pieces. And there could be, even when we talk about active inference, it's a relatively self-contained kind of model. It isn't like a cognitive architecture where you have like a speech center and it's just a general theory about certain types of human-like intelligent characteristics and how we can model them. So you can even have a deep learning. There are ways using amortized inference to even do active inference and learning the parameters with deep neural networks. You have universal function approximators.
Oh, fascinating.
You learn parameters.
Okay. That's
actually been like the earliest attempts at scaling active inference went in that direction.
Okay.
So they aren't necessarily mutually, they don't necessarily are incompatible with one another.
Right.
But I will say that active inference looks like it's going to be far more efficient and less cost and compute intensive than deep learning. So when you think about from a sustainability perspective, I would put my bet on active inference in the long term. It's not there yet because it has to be better. We have to prove that it's better than deep learning, right?
Okay, I've got to dig into that a little bit. Yeah, can you maybe just briefly explain what makes it computationally less expensive?
I think that's definitely an open area of research. Okay. I think that's not a completely well understood, but I would say, if I'm going to speculate, that it has something to do with the fact that the very nature of the specification of a generative model to begin with, and the way that you're designing usually deep learning. It depends what you're talking about deep learning, but deep neural networks, at least, usually we talk about those as discriminative models. So they're just figuring out. It's kind of a supervised learning type of problem. This is self-supervised. It's kind of an unsupervised sort of system. We talk about active inference, and the ability to the generative model essentially is able to represent or capture the data generation process. So that's in statistical terms, but what it means is, whatever is going on outside our heads is constantly generating data that we sense. If you can learn the structure of that process, then you can recapitulate it. And that means you're looking at causal relationships between variables. You're learning the actual causal structure of the models. You have more context. It's not like just pure pattern recognition.
Right.
We are very good at figuring out things quickly because we know how cause and effect works. So we can jump past all these other chains of logic that we need to make. We don't need to calculate all these variables to come to some conclusion. We just know how cause and effect works. We don't need to know, like, when I throw a ball that it's going to hit the ground. I just know that. I know it'll hit the ground. I don't have to calculate the exact equations of motion, for example. I just know that that's just the causal way that the world is set up. I think that's the biggest power of it and strength of it. And then as a result of that being data efficient, you also need less compute to actually run it.
Okay.
In theory, there's still more work to be done in that area.
Okay. Yeah, my mind goes to, as we're recording this, OpenAI released the Sora video generative model recently. And one of the videos that I think was most fascinating was there were two pirate ships fighting in a coffee cup. And what's amazing about that is some of the emergent capabilities of these generative video systems. It was doing ray tracing fantastically well. Yeah. The lights and the reflections were amazingly plausible. It was doing fluid dynamics.
Yeah.
Famously very difficult to model physically. And as you mentioned with active inference, these generative models, they have these powerful underlying representational systems so that you're not having to learn these things separately. They're kind of baked in. And my mind goes to the Sora model because none of those capabilities were explicitly delineated, programmed, right? They just fell out emergently from it having to learn to generate realistic video across all these different environments and circumstances. Okay.
Yeah.
Are there some common misconceptions about active inference out there in the free energy principle, whether it's in neuroscience or within the AI field that are sort of just common misunderstandings?
Yeah, I would say that the two that come to mind, or there's a couple, but I think one is that the first one is kind of, they're two sides of the same coin. One is that it's extremely complicated and too difficult and too hard to understand. And related to that is kind of the mystique that's sort of come around it. I think it's a fascinating field, and it does combine so many different areas. And that's been both its strength and its weakness, because if you want to explain something complex idea, the more fields you pack in there, the harder it's going to be. Right. And that has been, it's amazing because that's the whole, that's attracted so much attention. Its explanatory power is in that it unifies so much. But anytime you propose anything that's grand and unifying, you're going to attract people who are going to want to critique it naturally. And that's right. That's the process of science, right? So I think that's the first thing I'd point at, is that it's at its core, when you strip away the biology, when you strip away all the other fields that go into it, you're left with a really quite simple and elegant machine learning type of mechanism that any machine learning engineer would be familiar with in some sense. They would be dealing with time series type of data or partially observable Markov decision processes. It's all related to things that are very well known and understood. And so I think that's the first misconception, is like it's not as complicated as it appears.
Right.
It's still complicated because
it's still complicated. Yeah. I remember reading the Wikipedia page the first time, and it was complicated. But to stick on that point, it's such a powerful predictive model. To me, it's very akin to like evolutionary theory, which is, all of modern biology, none of it makes sense without that foundational theory of natural selection. It explains so much, but it took quite a bit of time for it to be generally accepted. So as we kind of wrap up here, I want to ask you about your book. Do you know when the first volume is going to come out yet?
Well, I know that I have to deliver the first draft in June, and there's some revisions. So I would say maybe optimistically by the early part of next year.
Okay.
Not quite sure yet. So it'll depend on, other work that needs to be done.
And that's the first volume, and then you'll immediately jump on the second volume.
Right. So the first volume is on active inference itself. What we've been mainly talking about here, we haven't really even touched on Bayesian mechanics, which is the second volume. That field, just to be clear, is a lot more theoretical and is in under development still. So whereas active inference, there's, the core ideas are probably fairly set. There's just going to be, a lot more work done to make it, to expand the scope of it and scale it. Bayesian mechanics is very theoretical. And if you're a person who loves the theoretical research, it's very exciting, as it's all based in this idea of physics of living systems, and incorporates a lot of other information from non-equilibrium thermodynamics and other fields. It's very cool, but it is a separate book that will be written in the future.
Okay.
and
Okay.
definitely have different editions come out as the field evolves.
Oh, I can't wait. As I said earlier, you were kind enough to share some early copies with me, and it's going to be an unbelievable book. Okay, well, we love to wrap up here by asking the same question, which is, if you could have AI automate something in your daily life, what would you pick?
Yeah, one thing that constantly gets in the way of me trying to just, live my life and spend time with the people that I love and write more is that the constant just things breaking down. So like suddenly, washing machine breaks down. Suddenly you have an appointment you have to make. You have to do this. There's always something that kind of goes on, and I think I don't like context switching. For me, I like to focus on a task for 3 hours without being disturbed, If I guess I'm looking for something like a personal assistant kind of AI that could do set up all my appointments for me, look at my calendar. And also if I have to get like a contractor to come over, they could take care of all that for me, and then I can spend time with people and do a lot of writing. I'm very happy.
I would love one of those too.
Yeah.
I can't tell you how much I appreciated this. It was great seeing you again, and I thank you so much for coming on, Sanjeev.
Absolutely. Thank you so much for having me.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.